for the main event today, we're going to continue this discussion of probabilistic methods for parameter estimation. So we did, okay, so the pen works here, good, kind of has to. We did this MLE method last time, and today we're going to do map and talk about some other methods that flow from that. As I said, we had the wrong order of these from my slides. People can see the slides, hopefully. So I'm in this new mode here. That won't work, okay. So the, how does this one work? The difference between this second method, the map method, and MLE is going to be that, excuse me, is that we're going to be dealing with more of the probability distribution, right? So, in fact, yeah, I guess this applies to both the methods. So remember what we're trying to do is we're trying to figure out these parameters, theta, that represent our model for the data to help us make predictions about it or classifications. And we know that the data we got is sampled from that, right? So there's some underlying distribution that just explains why it has these features and these values. What we're going to do is learn the parameters of that function, whatever it is, right? So we're assuming that theta is fixed but unknown, and then we have some other assumptions saying that all the data points we're getting are sampled independently from that distribution, and oh, that's why I'm repeating here, because I went to that slide for us to have the review. Good. All right. But this sets up, this is the same domain. So the thing we're going to change then we'll add, right? So we're assuming that the data is independently drawn from that distribution. We're going to estimate the best parameter, and we said that there's several ways that we can get this best, right? So what we did last time was saying let's find the parameters that basically make the data we saw the most likely possible. So let's come up with a distribution. We assume we know the distribution, sorry. So we say this is a Gaussian distribution. Let's pick the parameters of that distribution such that the data we've seen already is most likely, right? So now I'm going to jump ahead to slide 35, which gets us to this new method of map. I guess 34, I had a little intro. So map versus MLE, and this is when you have some prior knowledge about the distribution. Can you basically do something more efficient and more targeted? And that's what this method does. So we have the same idea that the data that generates, the distribution that generates the data is something that's in the world, and we want to predict these, we want to get the theta parameters of it. But now we're going to say, let's give ourselves the ability to have a prior on that data where we know something about the distribution a bit more. And this is our Bayes rule, right, that we've covered in one of the offline lectures, right? So what we want to do is to be able to have the parameters on their own. So how do we get we're trying to solve for theta, right? And we have D given to us, but we don't necessarily have these distributions given to us. So that's the question, how do we solve for theta? So each of these parts, kind of as we explained in that probability review lecture, have their own names. This prior is kind of the likelihood of the parameters themselves, and we'll see some different examples of that. But if we're saying that this is your distribution of your data is Gaussian, right? Then that means that the probability of the parameters is the probability of that particular value of mu, or the probability of that particular setting for sigma, right? So how likely is it that the mean is here, or that the variance is this? So you're talking about something a bit more meta, right? Like what is it, how likely is it that it has this setting? So what we're saying is if you want to basically just state this, and then we have this probability of the data, which we have to deal with, and then the real kind of probability of your model given the data is the output here. So Bayes' rule is a way for letting us to update our beliefs. We can use this rule in lots of different ways. We'll see them a couple times in the course, that basically you get some data and you can update your model based on new data you've seen. But those usually assume that the parameters are fixed and you're getting new data and you're learning. In this case, we're given the data and we're trying to estimate the parameter, right? And so what we're going to do is try to maximize the posterior probability, which is this, right? Of which is the posterior probability of those parameters given our data. I guess that's just a flip of the way they normally say it. All right, so the next slide has a different view of this. I'm kind of combining a couple different sources or versions of these that I've used or found. So what we're going to get to is the way for doing map versus MLE is this formulation. So we're going to talk about how we derive this. Basically, we're maximizing that parameter, but we've got these two components, right? So we've got a log of that prior on its own, which before was just written p theta. So I'm mixing notations here. And this one's still just the p. In the other slide, it was p of t theta. So for some reason, we're combining into logs and maximizing this thing, right? So why do we do that? So we talk about trying to solve for that parameter theta. We can write down the whole formula like this, right? There's our Bayes rule, here's the output of it. And we're going to say, well, we're going to put argmax on both sides and say somehow maximize for theta, right? So now we're going to solve for this. So if you think about, if you're just maximizing, because what's needed here, what Bayes' rule gives you is it usually outputs a probability, right? An entire probability. And the important part of this bottom part is that it does normalizing, right? It normalizes all of the values here so that they sum to 1, right? That's why it's important. They have to sum all to 1. In the previous slide, we had that kind of as an idea, right, that this probability at the bottom is really looking at all possible combinations of the data and all possible combinations of the parameters and how likely that the particular data would be with those parameters. But you have to sum over all the parameter values. If you have continuous parameters, and this isn't a sum, it's a integral. So it's very complicated to solve or impossible to solve, right? You're basically summing over every possible parameter you could have so that this thing will sum to 1. So long and short of it is that this is usually hard to compute. I'm going to erase some of this so it's not so messy. Another thing that people often call this, and especially in machine learning, you'll see this called, it's related to what they call the partition function. I have to go remember why it's called that. But it's basically normalizing everything. So it's usually hard to compute. So if we can avoid computing it, that'd be great, right? So since we're maximizing, we're just saying, I just want the highest setting of theta such that, we get the highest one, right? We don't need to normalize because we don't really need a probability. We don't need to know that this outcome is 75% and that outcome is 80%. We just need to know which one's bigger, right? And for knowing which one's bigger, for maximizing, the numerator is sufficient, right? So we can basically get rid of the denominator and say we're just going to maximize that. So then it's equivalent. We're still going to get the same value of theta. And then what we're going to do, and if you're, as we said last time, if you take a log, if you have a function and you're maximizing it, and then you take the log of that function and you maximize it, you're still also going to get the same point because log doesn't change the ordering, right? It's increasing dominant. So that won't change it mathematically either. So we take the log of both sides, and then we can apply the log and split them up, and that's how we get this function. So we're basically saying that we're going to maximize. Now we have two different components. And if you go back and look at the MLE math, it's, I guess that's what I have on the next slide, 2 slides up. This is the same as the one for maximum likelihood explanation. Sorry. It's the same one as for MLE, except it has this log prior term added to it, right? So basically map, we're adding this prior in to our calculation. Good. So what are some examples of how this gets used? So if you go back to linear regression, a very simple method that is not, you can argue whether it's really machine learning or not, but you have some parameters. If you've seen linear regression or not, you can go look it up. I'm sure you guys have done it at some point, right? You've got some variables y that you're trying to predict. There's some numeric inputs x that you're given as data, and you're basically just trying to fit a line to that data so that it is a good fit line somewhat, right? And all you've got is the weights of how important you're going to add. You're going to make each x point along the way, right? So you've got some line, and basically there's a bunch of x's, and the weights on the line adjust, how much you can move up and down the slope of this line so that you're fitting them all, right? So W's let you do that. But there's also some noise saying that you can be off by a certain amount. So we can represent this as a probabilistic model and then use MLE or map to solve it. So it's kind of the very simplest one you can do. Then we'll do a more interesting one, which is logistic regression, which is kind of the level classifier, which is related to kind of neural networks. So we just define this then as a probabilistic thing. We've got our noise. We're going to say our noise is Gaussian, right? So we've got our normal function with our mean and our variance. And the formula here, the model actually just goes inside the Gaussian. So this thing represents the entire, what we would normally have as that. It represents the entire thing, right? Because the parameters are kind of embedded, and then the fact that they're in this linear form explains this part of the model. So then we can talk about getting the probability of the output data as this Gaussian, and write out the Gaussian equation with our formula filled in, and that's what we have, right? So that's kind of defining it as a probabilistic model. And then if we want to use now these two tools we've used basically to invent linear regression using MLE and map, you get these two different formulations. We say we want to maximize the weights, and so when you derive it, and I have the derivation slides for this in more detail are at the end of this slide deck, so people can look at it to kind of go into it in more depth. The negative comes out, so we're actually going to be minimizing the weights rather than maximizing them, but the intent is the same, so we're kind of doing these calculations for each of the values along the way, and solving for the weights. And like we talked about last time, when you actually want to solve it, there's different ways you can do it. If you can take the analytical form of the equation, then you take the derivative of the formula that you have. Oh, you can't see my mouse thing. You take the derivative of the formula you have, you set it to 0, and then you solve for W, and that's how you get these weights. Sometimes you can't analytically solve it easily, and then you have to kind of iteratively update these. Right. So in this case, we could solve it exactly. That's why linear regression is kind of the way it is, kind of this standard tool. And so each of the two different forms we have there lead to different kind of versions of linear regression, right? You kind of have this unregularized version, and I guess when we solve for the mapped version, the prior comes out into its own component, and so essentially you're adding something that improves the robustness of the model. Right, so we talk about things being regularized, and this will come up again with more complex models. I guess I have a slide on it. later. Oh yeah, for map, we have it again.
Is me a professor?
Yes, someone's talking. Okay, we can do that.
Yes. Sorry.
Yep.
I just had a quick question.
Yep.
On here, when it says that the prior distribution acts as a regularizer, usually when you have a regularizer, that should be a variable, but the prior should just be a constant. So how does it act as a regularizer?
Well, the prior doesn't have to be a constant necessarily. It can be an entire vector or its own function and have its own priors. So it doesn't have to just be a number. In this case, it's not, how does it get to that state? Because the prior for us is that we're just giving it the mu and the sigma for this setting. I mean, the way that a regularizer works in general, the fact that it's on the end here, basically you've got the core kind of method you're trying to optimize, and then you have this additional part which is a regularizer. And what it does basically is that it penalizes the answers being too far, having too much variation, right? So if the variance of these things goes higher, then you've kind of added another penalty term because you're trying to minimize this entire function whenever this will be high when the weights are highly correlated. So if there's lots of zeros, then this would be lower, but if they're all kind of larger numbers, it would go up, I guess. So you're trying to focus on, I think, getting a small set of weights that really solve it rather than having the solution distribute across all the weights. And so in that sense, it's a regularizer because it's adding a penalty cost on the core function. But a regularizer can be anything like this, that where you're adding an additional kind of orthogonal cost on top of the thing that you're optimizing, because it's trying to basically, it could be something that's trying to minimize variation, or it could be something that's trying to make sure that only a small number of the variables are being used. So the more that there are zeros and ones, it's better.
Sorry, what does it mean if, what do you mean if W is highly correlated, right? Like, this is just a dot product with itself, so it would always be correlated, right? So here you have a dot product with W, and then you have lambda, which is some hyperparameter, right?
Yeah, I guess I'm saying because if it's crossed with itself, so I'm trying to think when it would be higher. I didn't think through what it would be. If there's more zeros, right, this would be lower, right? Because many of them, the elements would come out lower within the vector. So if you can fit the line with just a small number of points, then it would be better in terms of this regularization.
Oh, I see. Okay, yeah, okay.
That's what I'm getting at. I could be wrong. We can go check it deeper. But yeah, I mean, it's correlated with itself. So it just mean that the values are going to be added up, but they're yeah, so it's, I mean, you're trying to say also, I guess, that if you think of the vector, the weight vector that you're using, you're trying to say that it has this, it doesn't have a very large spread in values. If you think of that vector as a point in space, then it's going to be, you want it to be smaller. But we have to think about different ways what the intuition of that means. Right, but if you want to put different, regularizers on here, you can get different versions of this equation, even though you're not going from the previous formulation. So these kind of tricks are, common in many different methods, and the idea of that regularizer will come back in some of the other methods we have, but we'll cover it more deeply, so we'll make sure we cover that better. Linear regression map. No, so I mean, I had, like I said, we have the more detailed slides at the end on this derivation. So here's the way they got that. So that lambda is the variance for the distribution. So they're not using a normal sigma, so that's why it's confusing. And then they have the Gaussian distribution. They kind of derive out that formula for the log. They just break them out. And then when you're trying to maximize it, same kind of thing. Some things aren't relevant because they're not going to change which one's the maximum, so they can kind of be dropped. This distribution that's based just on the data isn't going to affect the final answer. You only care about things that are dependent on the parameters. And then I guess this is when they get the derivative of it and work it out. And again, because there's a negative in the formulation that they work out, they kind of switch from max to min. And then, yeah, so I guess look at that. There's more detail on that. Maybe that would help understand that. Is that when you said that the variance sigma is set to 1, then it's equivalent to regularization, but it's not for all values of that. So in certain cases. So you can get kind of least squares and other versions of linear regression out of MAP and MLE by kind of putting in different variable settings for this. So it's just, the reason I'm just showing it is that it kind of, to put it as, that some of these classic methods can be generalized within these models.